Good afternoon, everyone. So, uh, I'm Kiran. I'm the VP of Engineering for HighLevel, and with me, Pragnesh, our staff engineer. So, we want to walk you through on what are challenges that we started out with, and then how we ended up, and then where the outcomes are, and what the journey looks like. So, about HighLevel is a ultimate marketing platform for the digital marketing agencies. We have 90,000 agencies on our platform serving about 3 million uh, small businesses across multiple geographies. And we serve about 4 billion API requests every day. And we have, to let you know the scale of what we are dealing with, uh, we have about 2.5 billion message events that are processed within the platform every day, and about 250 terabytes of database, and almost a little over 250 workloads that process all of this data across the board. So we also have a billion host names or million websites that we host for our customers. So the challenges that we had, so if we look at it, like we are serving about 5 different data stores are used to serve all the databases or the data to the customers and process it. Within those, we have 3 different databases that gave us challenges. Each of each of it has its own set of challenges. One, MySQL, we were scaling up, and then it was not. It was at a pace where it is crawling, and then it is not responding to any queries. The other one is Elastic, and then we ended up resharding it over and over again so many times that we almost gave up. And the next one was Mongo, where we had to add so many indexes that the index size is more than the actual data size. So all of these challenges actually pushed us to look at where we need to invest and then where we need to go for going forward. And our order of priority for what we wanted to do and then where we wanted to invest our time is pretty set. So we wanted high throughput, low latency, and then low operational overhead. Because of what we have seen with Elastic, what we have seen with Mongo and MySQL, the operational overhead is a given, and then the ease of archival. So all these did not provide an archival mechanism that is easier and queryable at the same time for us. And so the purpose built time series for some of these logs that Pragnesh will be talking about. And then the cost is more of a outcome for us or a byproduct. So we were not looking at cost because we wanted to serve the customers first, then look at the optimizations, but cost was a byproduct for us. So with this, I'll hand over to Pragnesh to walk us through on the use cases and then how we managed to move.
So the first use case is the leads activity, which is users engagement that we are actually storing in the databases. We have started with the MySQL, and at the peak time in the MySQL, we had 11 terabyte of data, daily 30 million inserts that were happening, 150 reads per second. And this reads per second was really a problem for us. Why is it a problem? In some cases, when the contact or a lead is having too many activities, it is going to create a latency issues in the read areas. And the latency is sometimes going into like 50, 60 seconds and sometimes timing out for users as well. So this is one of the biggest problem. And because of the 11 terabytes data and 12 billion records, the table size was so large. Let's say if I need to add one more activity inside the MySQL table, and if I need to add one more column, it's very difficult for me to add one more column. And creating an index is you forget about it on top of it. So high maintenance during the during upgrade or during any maintenance activity, and timeout errors. So we started exploring ClickHouse. We saw the first thing is storage size reduction. And when we migrated fully to the ClickHouse, we saw that our 11 terabytes data became 1.3 terabytes. It's a whooping 80%, 88% reduction in the storage. After that, we have storage and compute, which is separate in the ClickHouse. So we don't worry about now like scaling compute as we want. Basically, if our traffic is getting more, I mean increasing, then we'll just increase the replica over there and we'll be good with. And the third last part, which is the best desired one, which is sub milliseconds latencies for our users. And I'll show you the results as well. Uh, Before with the MySQL, the P99 latency was 6.14 seconds, and there were 5xx timeouts, as you can see below, where the latencies are going up to, with the 200 as well, the latencies are going up to 59.20 milliseconds. After 59 seconds, it is going timeout. Uh, so after introducing ClickHouse, every query is resulting in, I mean, we are getting P99, which is below 200 milliseconds over here. And most of our no 5xx is the great achievement for us. And I mean, some of the queries which are going around 1.5 seconds, which is a maximum latency. The second use case is workflow logs. So we have one product which is workflows, where we allow customers to create automations, and when they create automations, there are execution logs at each step of the workflow, and these logs are stored inside the workflow logs. The scale is 1 terabytes per day, 600 million records, which is 6 million records, 2x growth every year. We started here with my Mongo database. We realized in 6 months that it will not work with the Mongo at all. We migrated it to Elasticsearch at that time. In Elasticsearch, the problem was every month we'll need to increase nodes over there. So let's say today we have 12 nodes. In next month, I'll need to increase 2 more nodes over there. And uh, uh, we were not seeing any impact on the CPU usage. CPU usage is staying below 10% over there. Just to increase the EBS size, I'll need to add more nodes over there. To get away with this problem, we have migrated this use case also to the ClickHouse. 60 terabyte data in Elasticsearch became 6.27 terabytes, again around 90% of the storage reduction. And we were like 12 is a star, I would say. The storage, the nodes which we were running was around 25 nodes at the time when we completely migrated to ClickHouse. And now we are just running with three replicas of the ClickHouse. That's it. So, I mean, completely storage and compute isolation over here. The third use case is a very interesting one. I mean, till now we had just migrated the data, which is immutable data. Here with notifications, the challenge was the data is immutable, but still there are reads and the deletes that we need to store. So when the user clicks on notifications, we need to store that whether the user read the notifications or not. And when a user is deleted from the database, or a note, I mean, a complete customer is basically deactivated, we delete the notifications over from the table. So these are the two challenges we were exploring, whether we can use ClickHouse or not. And notifications is like kind of split between two databases in our infrastructure. One is Mongo and one is Firestore. So we started with Firestore. Firestore is our primary database in the notifications, but we Firestore is not able to do count and complex aggregation queries. So we moved the 3 months data, which is what we show it to the customers, to notification to Mongo database. In Mongo database, we were just vertically scaling the databases whenever we see the increase in the index size, or increase in the disk IOPS, increase in the CPU usage. We reached up to like 48 vCPUs in the Mongo database. So to solve this problem permanently, we started exploring ClickHouse over here as well. We created 3 tables, one for storing the raw data of the notifications, which is not changing, merge tree engine. The second is where we are storing the flags, which is EaseRead and the deleted one. And this can be changed replacing merge tree. And whenever user clicks on, or there is a deletion of the user happens, we insert the data over here. And the third one is whenever the customer. So if you see over here, the order bys in both the tables are user ID and date location ID, or user ID and data ID. In the third table, we have the order by, which is location ID and contact ID. Why? Because whenever the data deletion comes to us, we need to delete it by the location ID or a contact ID. At that time, we don't know what is the user ID for which we need to delete the data. So uh, this is the materialized view. So we created this table for a materialized view, and we are storing that data. So at the end, we need to insert the data inside this second table, which is replacing merge tree whenever there is a use case of the location ID or a contact ID delete. And these are the queries. Here, there was a good discussion that happened uh, around this five of the learnings. The first and the fifth I'll explain in one go, which is how to partition a data in notification. So what we have started with exploring that whether we can use 7 days partition, 15 days partition, or a 1 month partition, or a 3 month partition. So I mean there are a few choices. We need to show the 3 months data to the customer. So we have started with 7 days or 15 days. Then we thought that it will be like 24 or 12 partitions that I need to scan every time to read the notification. So we have gone with the monthly 3 months as well. And then we landed up on 2 months because 2 months size is also less. And 2 months, I'll just need to scan two partitions to get the data. After that, we use the so in the previous slide, if you see the query, second query status join, we were using final in here. By using final, uh, it was creating so much of a merge joins at that time. So and it was degrading the performance. And we came to know that there is a one more option which is argmax over here, which we can use, which is very efficient. I mean it I mean I would say increased our performance by a lot. Use the bloom filters for selective fields, and avoid using the wide materialized view for the hot counters. Here also the same benefits, storage reduction, and we don't need to horizontally vertically scale any database instance now. The performance is quite impressive over here. In our peak times, which is between 7 p.m. India time to 4 a.m. India time, we are seeing that the query latency is above 4 seconds only. And after introducing ClickHouse, every P95 latency is below 500 milliseconds. So I mean, great improvement on the latency side. The fourth and the last use case is about the revenue dashboard. So this is kind of a uh, usage billing dashboard that we show. So around the use case, it is the data of billing for our customers and customers as well. So what we were doing is we were ingesting data in Mongo for a transaction. Then on a daily basis, there was a cron which was inserting again the data in Mongo. And in the Mongo only, we are like having a queries which which is powering the dashboard. I mean, it was 1 day delay data as well as not scalable approach. I mean, in the Mongo, it was not able to do a lot of aggregations on top of that. So it's simple architecture right now where we insert the data into GCS through the pops up. That basically scans the data and inserts into ClickHouse. And then we have a materialized view on top of that for every dashboard that we want, and that is powering our agency dashboard for billing. The scale is 70 million plus batches, uh, 40 million real time record insertion, and materialized view. We are leveraging everywhere for powering the dashboard part over here. And latency is, I mean, in P95, latency is around less than 400 milliseconds, except that spike, it is less than 200 milliseconds. And the last but not least is client side observability. So in high level, what I mean, this is a normal problem that there are multiple microservices which is connecting to the one data instances. So what happens is we don't know which instance is actually which microservice is calling this, how much APIs or how much database calls that they are calling, and what method that they are using. So we have a baked in a client side library, which will be able to show you what instance, what table, what query that they are doing, and what is the application that is it is doing. So basically, the counter part, latency part, and histogram of latencies it will show to you. based on the table. And how we are doing it is basically using a proxy of simple Node.js. So we wrap around the method of the ClickHouse query, insert, execute, and command, and we ingest the data into Grafana and achieve this observability. At the end, what are the lessons learned? No update heavy data except notifications that we have did. Uh, Optimize primary key and order by partition. I mean, we make sure that whenever we design the data tables, we make sure like it goes to the 2-3 iterations before going to the production to make sure that the schema and the partition key is very optimized, insert in bulk, and making sure that more and more observability in case if we need to debug things further. That's it. Thank you so much, everyone.